Welcome to RBE1001 Lab 2. Today we'll be going over driveline performance, method writing, and how to use an oscilloscope to measure waveforms. The goals of this lab are basically to have you understand spur gear design and how it'll affect the speed and torque of your robot and how it'll affect the driveline performance of it. We want you to be familiar with how a DC motor performance will affect the overall performance of the robot. Next, we want you to be familiar with how to program different functions for your robot. The last step is to teach you how to use an oscilloscope to measure waveforms. As always, with every pre-lab, we would like you to read through the entire lab before you come to the lab period. It's very important that you understand the assignment so that you can ask intelligent questions. We would also like you to think about the final challenge before this point so that you can start to understand what you'll need to do to complete the final project for this class. As we start the lab, the first step will be to calculate the forward travel per motor revolution for the robot. We also want you to calculate the speed and tractive force of the robot using a 95% efficiency on the gear train. Once you've finished calculating all of those and filling in the chart below, we would like you to basically configure your basebot with the 3 different gear ratios and actually measure the speed and force applied by the robot. There'll be spring scales available and there will be tape measures on the fields out in the other room so that you can measure how fast your robot is going and how much force it actually applies to the ground. We would like you to describe any discrepancies you had between your calculated data and your actual results. Part 2 of this lab will be writing different methods. The first method we would like you to write is the drive straight method. We'd basically like it to be able to take in an integer of distance in inches and have the robot drive that. You will be dead reckoning, which basically means just using a time estimate to see how far the robot drives. Once you've completed this method, we'd like you to actually try it out. We ask that once you write the function and get it to the point where you want it, you do not change it for step 4. So you use the same set of code for all the different distances in part 4. Then we'd like you to describe any inaccuracies that you found and what you can attribute them to. Lastly, we would like you to think about what you could do to make this method more functional. What would make it more accurate? So would adding a certain sensor or measuring the battery voltage or something along those lines make it more accurate? Think about it and write down your answer. Part 5, we're going to have you do a similar exercise where you write a square method. We basically want to input the length of a side and have the robot drive a square. It's best to use a for loop here and have it stop after the 4th side. We do want to see the robot actually come to a complete stop. For part 6, we're going to have you write the spiral method. The spiral method, it doesn't matter if the robot starts in the center and works its way out or starts on the out and works its way in. I will say from my experience, it works better if you ramp yourself down to spinning in place. That way it's easier to not drive off the table at the end. You will need to get a TA sign-off for parts 5 and 6, so you need to be able to show this to one of the TAs, SAs, or myself, so plan accordingly using the class calendar. We would like you to then discuss what you could do to make these functions more generally useful, especially the drive straight function. If you look into the WPI lib drive functions, it'll give you a hint of something that you could do to make this function a little bit more robust. The next step in this lab will be using the oscilloscope to basically measure different waveforms. The first part is the calibration waveform that's available on the oscilloscopes. We'd like you to hook up the scope probe to the calibration waveform. There's a small metal lug on the front of the oscilloscope and basically record all of its different values. Part 8, we're going to have you measure the PWM signal sent to the servos or servo motors. We would like you to see the full forward and the full reverse directions and write down all of the different characteristics of those waveforms, and then interpret your results. Lastly, for part 3, we would like you to hook up one of the VEX servos to a potentiometer, and then record the output as you rotate the servo from 0 to 180 degrees and back. We'd like you to figure out the settling time, so how long the servo is actually moving between each of these transitions. And then we want you to interpret your results. As is with all of the labs in the 1001 course, we have an appendix to help you through it. This is just information and background material to help you guys get through the lab, and also shows descriptions for the individual problems. The first part is just an introduction and covers the objectives of this week's lab. The second part here describes the waveform measurements. With waveforms, it's extremely important to include all of the labels. If you don't include the labels on a square wave, then basically you're going to get 0 credit for it, because a square wave isn't very descriptive unless it has its labels. The most important labels that we have outlined here are your V positive, your VPP, and your VP negative. What those are is VPP would be the overall voltage change in your signal from the lowest point to the highest point. VP positive would be the difference between ground and the highest point, and VP negative would be the difference between ground and the lowest point. So those are measurements for voltage, which is in the vertical scale. The other labels that you'll need are for the horizontal scale. So you'll see that there's time high, time low, and time period. The period is the amount of time it takes one cycle to happen. The time high will be how long the cycle or the signal is high in comparison, or just in time in general. The duty cycle will be a comparison of the time high over the overall period. There is such thing as the negative duty cycle, which would be the time the signal is low compared to the overall period. So once you calculate the duty cycle, we'd like you to include all of those labels and measurements both on your diagrams and in the lab worksheet. The oscilloscopes that we have in the lab are the new TBS 2072 series. They're Tektronix scopes, and we've included the XYZs of oscilloscope PDF manual on the lab page in Canvas. As part of the exercises, we would like you to basically read certain chapters in that oscilloscope guide. The three main functions that you guys, or the three main areas that you guys are going to have to adjust on the oscilloscopes are the vertical control, so basically how much voltage per channel or per division. With an oscilloscope, the vertical measurement is basically volts per division, or millivolts or microvolts depending on the signal. The horizontal scale is basically the time period. You can adjust the time period all the way down from nanoseconds to full seconds. I will note with the Tektronix scopes, they don't do a very good job of capturing slow waveforms as far as triggering. So triggering is basically the function of having the oscilloscope capture a wave and keep it squared up and centered in your screen when a certain signal happens. So the trigger is usually set at a voltage level, so as the signal changes, it'll basically move that change to the center of the screen so that you can properly see the signal. As I said, with the really slow waveforms like the servo response, you basically won't be able to use a trigger, and you'll just have to time the start and stop button on the scopes effectively. It is really important that you understand how to use the scope and don't just use the auto set button. The auto set button won't work on the slower signals, and it doesn't really build understanding on how to use the oscilloscopes. For the actual lab practicum, we have the different pages that you're going to read, 7 through 12, 19 through 21, 37 through 40, and 40 45. These pages are basically the most important part of the guide. I do want to note you do not have to compensate the scope probes. All of the scope probes have been compensated before you got here and calibrated. If you try to compensate them, then you'll basically cause problems for other students and be doing a frivolous exercise. At that point, we'll have you hook it up to the different signals. The one thing that it noticed that is written in the lab that I would like you to do slightly different is it mentions basically rotating or changing the servo signal from forward to reverse every other second. That makes it really hard to capture a waveform, so what I recommend is putting one channel on full forward and leaving it there, and put another channel on full reverse and leaving it there. And that way you can measure the signals. As is with the servo library, it's very important that you do not call servo.write faster than every 20 milliseconds. If you call it before it has a chance to respond or output the signal, then basically it will never output the proper signal. So make sure you have a delay in your loop so that you don't call the function too often. The motor ports on the shield are the only ports that are fused with the 7.5 amp fuse, so you will be dealing with a higher power than all of the other ports on the shield. With that said, be careful not to short it to ground or you will blow a fuse, and that's why it's there, to basically prevent things from getting damaged. The 3-wire connectors for the servos are power, ground, and signal. The ground wire is black, the power wire is red or orange, and the signal wire is white. We basically want you to plug the servo into a breadboard and then use wires to connect the breadboard over to the oscilloscope and to the shield so that you can take those measurements. We want you to look through the appendix, and also know that all of this information is available on the lab wiki, wiki.wpi.edu/robotics. The last part, where you hook up the servo to the potentiometer, we ask that you don't fix them together, but you do hold them steady. The reason we do this is because a potentiometer can only turn a certain amount of degrees, roughly 270 degrees, and if you don't align them correctly, then basically it's possible to break the potentiometer if it was affixed firmly. So we ask that one person basically hold the servo and the potentiometer still, while the other person is capturing it on the oscilloscope, so you will need two people. You can see the breakdown of how to make the connections here for the potentiometer and the for the servo and the potentiometer. With the potentiometer, there should be 3 wires, a black, red, and ground. With potentiometers, it's usually set up about 95% of the time, where the outside 2 pins are the overall resistance, so power and ground, and the signal is on the center pin. Now, that is for the physical potentiometer. For the actual wire, we always wire it so that it can plug into the shield, which will be ground power signal. So you need to pay attention to which wires are connected where so that you don't short out the potentiometer. If you connect the potentiometer wrong, where you connect power to one side and then ground to the center pin and adjust the potentiometer, you'll get into a scenario where you get 0 resistance and the potentiometer will burn out and smoke and let out the magic smoke, as Ken likes to describe it. The last part here describes the driveline performance and shows you the individual equations for completing the calculations for your driveline performance. It talks about the gear ratio, the tractive force, and the overall torque that the robot will be able to apply to the ground. For the last page, it basically has the motor data information from the VEX website. What we would like you to do is use the most efficient range of the motor, so roughly 90 RPM, to estimate your calculations. So that is the numbers for your torque and speed that you would use to basically figure out what your robot's going to do. Now, you will see certain scenarios where these numbers don't necessarily make a lot of sense, and your calculated value will differ from your actual value. The most extreme one is when you have a large gear on your motor and a small gear on your axle for your wheel. Basically, the motor will be in stall for that entire period of time that you're accelerating, which will probably be almost the entire 5-foot distance that you're driving. During that time, the motor is basically at stall, which is a bad state for a motor, and it's creating a lot of excessive heat. And you will notice that if you basically overheat the motor, that it has a thermal sensor inside, and it'll take about 10 minutes before it actually gets its full torque back. So try to drive it as short as possible when you're in the gear ratio with the 60-tooth gear on the motor and the 12-tooth gear on the axle. Outside of that, I would like you guys to have fun this week. Robotics is supposed to be enjoyable, so have fun, and I'll see you back next week.